Look up at the night sky, what do you see? You see history. You see light that has traveled for years, centuries, millions of years to reach your eyes. This light is the universe's ultimate messenger, racing across the cosmos at a speed so immense almost impossible to comprehend. This isn't just fast, it's the ultimate speed limit. Albert Einstein taught us that nothing with mass can ever reach it. This number, nearly 300,000 kilometers per second, or about 186,282 miles per second, is woven into the very fabric of reality. It's the constant, the benchmark, the one true speed that governs everything we know about space and time. It's the speed of light in a vacuum. But what if I told you that this ultimate speed limit isn't always the speed of light? It sounds like a contradiction, a cosmic paradox. Yet, this is where the story gets truly interesting. The universe is not just an empty void, it's filled with galaxies, stars, planets, and even the very air you're breathing right now. When light journeys through these different substances, something remarkable happens. It slows down, that's right. The fastest thing in the universe isn't always moving at its fastest speed. Let's get specific. How much does light actually slow down? In the vacuum of space, it's our familiar 299,792 kilometers per second. We call this constant c. But let's send that light beam into a different environment. Water. Inside a calm pool of water, light travels at only about 225,000 kilometers per second. That's a 25% reduction in speed. It's still mind-bogglingly fast, but it's no longer c. It's as if our cosmic sprinter has decided to take a leisurely jog through a more scenic and crowded park. Now let's make the journey even more challenging. Glass. Typical glass slows light to roughly 200,000 kilometers per second. That's a full 1/3 slower than its top speed in a vacuum. The densest material of all, a diamond, puts up the biggest fight. When light enters a diamond, its speed plummets to just 124,000 kilometers per second. That's less than half its speed in empty space. This is precisely why diamonds sparkle so brilliantly. They bend and slow light in such an extreme way. Scientists have a name for this property of a material, the refractive index. A vacuum has a refractive index of 1, our baseline. Air is very close to that at about 1.0003. Water has a refractive index of about 1.33. This means you divide the speed of light in a vacuum by 1.33 to get its speed in water. Glass is around 1.5. Diamond has a very high refractive index of about 2.42. This brings us to the big question. Why does light slow down? Is it getting tired? Is it losing energy as it plows through atoms? The answer is a beautiful and subtle piece of quantum mechanics. Photons never actually slow down. Between one atom and the next, a photon is always, and I mean always, traveling at c. It knows no other speed. So what's going on? The slowdown is an illusion. A constant, incredibly rapid dance between light and matter. It's a game of absorption, it's a game of re-emission. Imagine a photon entering a piece of glass. It zips along at c until it meets an atom. The atom's electron cloud absorbs the photon's energy for a minuscule fraction of a second. Think runner in a relay race handing off a baton. For that moment, the photon ceases to exist as a traveling particle. Its energy is held by the atom. Then the atom re-emits a new photon with the same energy and direction. The new photon zips at Ca to the next atom. This happens billions upon billions of times as light crosses the material. Each interaction adds a tiny, almost immeasurable delay. So although photons travel at Ca between atoms, the total transit time through the material is longer than in a vacuum. It's like a tourist in a crowded city. Walking speed between points stays the same, but stopping to take pictures lengthens the trip. Now, let's take this concept back out into the cosmos. We've established that matter can slow the effective speed of light. But there's another cosmic force that can affect light's journey: gravity. According to Einstein's theory of general relativity, massive objects like stars, galaxies warp and curve the very fabric of space-time around them. Think of it like placing a heavy bowling ball on a stretched-out rubber sheet. The sheet sags and curves around the ball. This is what massive objects do to the universe. Light, aiming to travel straight, must follow those curves. When light from a distant galaxy passes near another massive galaxy, its path is bent. This phenomenon is called gravitational lensing. From Earth, it can make that distant galaxy appear in a different position, or as multiple images. It's like looking through a distorted, cosmic-sized magnifying glass. The universe becomes the lens. Here's the subtle distinction. Locally, at any point on its curved path, The photon still moves at speed c, however because it must take a longer curved path. So we return to where we began with a deeper appreciation for this fundamental constant of nature. The speed of light in a vacuum, c, is more than just a number. It is the thread that ties together energy and matter, space and time. It is absolute. A photon of light born in the heart of a star billions of years ago travels at this exact speed through the void. It does not age. It does not tire. From the photon's perspective, no time passes at all between creation and the moment it strikes your retina. It is timeless. The apparent slowing of light in materials like water or diamond isn't a violation but an affirmation of the complex and beautiful ways light interacts with the universe. The endless dance of absorption-re-emission is a testament to the quantum nature of reality. It's a process that delays light's journey without diminishing its energy or changing its fundamental properties. If this journey sparked your curiosity, subscribe to Universal Universe, share with a fellow traveler, and give a thumbs up.